it is difficult to describe how great a pleasure is for me to be able to talk here and to start with congratulating Endre to this great prize that I have known Endre since I was a student, and he was then just a young researcher who was kind of a hero because we knew that he had fantastic results, and he was one of the very successful younger people who were, well, sort of a generation, a university generation ahead of us. So it is really such a pleasure to be able to congratulate now to him. So I would like to talk about the many facets of the regularity lemma. Let me start with an old story about 150 years ago. There was a Hungarian poet who was very well known, János Arany, and at some point, he was also a very modest man, and at some point he had to sit through a talk where the speaker was speaking about about him, about his poetry, and he said, yeah, when that's the poet thought this when he says that, and he thought that when he says that, and then he answered with a very short Hungarian expression, gondoltam fenét, which to English it translates something like, well, did I think that? No way. And so I think Endre will maybe say this thing, but I think that if there is a discovery which then inspires people to extend it, and then it extends to a number of directions, to probability, to analysis, to number theory, and so on, then probably the original person who thought of this had the depth of his thoughts are penetrating other areas, and it's not his job to think about all of those. It's our job to think about all of those. So here is one aspect that also Endre formulated in his talk. And it says that it's a quote from Terry Tao's plenary lecture at the Madrid Congress, a famous theorem of Szemerédi asserts that, and I will not quote the theorem, we have seen it and we will see it. And he says there are many different proofs of this deep theorem, but they are all based on a fundamental dichotomy between structure and randomness, which in turn leads, roughly speaking, to a decomposition of any object into a structured, low complexity component and a random, discorrelated component. So this is one way of looking at it, and Endre formulated a somewhat similar philosophy of this regularity lemma. Maybe I will show that there are maybe 2-3 other ways of looking at the lemma, and they are all very fruitful. So here is a statement of the lemma. I will try to explain what the lemma exactly means, but it's not that easy. The nodes of any graph can be partitioned into a small number of essentially equal parts, so that most bipartite graphs between two of the parts, so you take two of the parts, you look at the bipartite graph between them, are essentially random, but for different pairs of parts they have different densities. Now I will try to make this more precise. So first of all, to be able to state it, we need some epsilon, which is an error tolerance. So this is about approximation. So you have a huge structure, a huge graph in this case, which is probably the simplest large structure you can think of. And you have this very large structure, and you would like to understand, have somehow an approximation of it by something simpler. You want to understand its structure, but so you want something simpler. And so there is an approximation, and whenever you talk about approximation, you have to specify a tolerance for error, and so this is an epsilon. And now, what does it mean that you partition it into a small number? Well, I think the small should have been put in quotation mark here. The number of parts is k, and well, the lower bound, I put 1 over epsilon there. It just excludes some trivialities like putting everything in one class. 1 over epsilon is perfectly fine as a lower bound. But the upper bound is really, cannot be considered that small, but it's a tower. It's 2 to the 2 to the 2 to the 2 to the, and you have to go 1 over, I don't know, epsilon squared, or sometimes epsilon to the fifth. It depends on other details, which I don't want to go. So 1 over some power of epsilon height. So this is really a theoretical result in this sense. Although at the end of my talk, I'll probably be able to point out that sometimes the situation is not as bad. So anyway, but it's a finite number which depends only on epsilon, and that's the crucial thing here. Now let's go on. The essentially equal parts means that that's actually easy. It just says that maybe you cannot really partition it into equal parts because of divisibility, and so, but almost equal. The difference between any two cardinalities is at most 1. Now, what does it mean, most bipartite graphs between two parts? Well, we allow some exceptions. The number of exceptions is epsilon times k squared. There are k squared or k choose 2 parts, and so an epsilon fraction of them we allow to be exceptions. And now the essentially random is a somewhat technical issue. I formulated one possible way of looking at it. It says that if you take 2 of these parts, vi and vj, and now you take 2 subsets, x and y, and you count the number of edges between x and y, then this is Pij. This Pij is the density. It's the fraction of pairs that are connected between Vi and Vj. And so between x and y, you see the same fraction of pairs connected, plus an error term, which is depending on epsilon. So this is what it means that it's essentially random. So this is the famous regularity lemma, and it has many forms. And so Andre was denying that this is really the same as the lemma in his number theory paper, but since it has many forms, I think one could argue that maybe the number theory version is the first appearance of this lemma. So anyway, there is the original regularity lemma that I formulated, and there is a weaker version of this regularity lemma, which is very important and which was found by Frieze and Kannan in 1999. Now you may wonder, why does anyone formulate a weaker version of a theorem more than 20 years later, and of a result? And the point is this tower. So the Frieze-Kannan version of the lemma does not contain a tower. It's just simply, 2 to the 1 over epsilon squared, which is still a large number, but certainly it's not a tower. It's something that we are used to. I mean, it's in that range. So this is the importance of the weak regularity lemma, plus the fact that it has a somehow, in a sense, simpler statement, as we'll see. But then people have also strengthened the regularity lemma, and there are, again, a number of these. they are more or less equivalent to each other. The first one was formed by Alon, Fisher, Krivelevich and Szegedy in 2000. And it's a very useful version. And then there are other versions due to Tao and also Balázs Szegedy. It's a different Szegedy, brother Szegedy and myself. I will talk about these. So let me first start with explaining this weak version a little bit. So suppose that, so it's also about a partition. So we partition the graph into classes, and the number is now more decent, maybe 2 over epsilon squared. No, 2 to the 1 over epsilon squared. And let Pij denote the density of edges between Vi and Vj. So what fraction of edges is present? And this weak version says that if you take any set S, then you pick any subset S, and you wonder how many edges should there be in this set? How many edges should be induced by this set? And what it says is that you can sort of, maybe I'll point it. Yeah, okay. So this sum here is what you expect. So this is the fraction between the part of S in SVI and the part of S in Vj. And so this is what you expect to see, the number of edges. And that's what you actually see. And the error should be, again, bounded or by epsilon times n squared being a trivial upper bound on the number of edges. So this is again, an approximation statement, but basically instead of bounding these kind of numbers separately, it just bounds it on the average. The big gain is here in the cardinality. Another way of saying it, and this will be important, is that so what we can do is we can replace the edges. So suppose you take 2 of these classes and you erase the edges between them and you put them back in randomly. So suppose you make an error, you erase all these edges. Now oh my, what happens now? I mean, I have lost my graph. And so but you remember how many edges were there, and you put back the same number of edges, but you don't have any other information, so you put them back randomly. And suppose you do this for every pair. And the statement of the lemma is that after that, the graph you got is very similar to the original. So this new graph G prime, one way of saying that they are similar is that if you take any set S of the nodes, then this set S will contain about the same number of edges from both graphs. And this is an important way of looking at it from an algorithmic purpose, because what it means is that if you want to remember some huge big structure, you want to remember only some small number of data, so that from these data you can reconstruct the structure, or at least some other structure which is very similar to it. Then all you have to remember are these Pij's, these densities between the classes, and of course the number of classes. So this is kind of a result about making your data compact. And let me point out that this is a way that one would very much like to do in the case when the graph has a smaller number of edges. So this is a technical technical point, but this lemma, the regularity lemma, concerns graphs where a positive fraction of the edges is present. So dense graphs where say, I don't know, 25% of all possible pairs that could be connected are connected. Now, unfortunately, most real-life graphs are not like that. In most real-life graphs like the internet, the number of connections is much smaller. It's a negligible fraction of all possible pairs. And a similar description of those graphs is still not at hand. So it's a big unsolved problem how to extend this to the case when, say, instead of constant times n squared edges, only constant times n edges are present, and you would like to give a compact description of these graphs in the spirit of the regularity lemma. Now, the original version, as I told you, it's about bounding these numbers separately. So you take two of these classes, and then you can sort of introduce some measure of irregularity between the two classes. You pick some two subsets, x and y, and you see this is the number of edges you expect to see. That's the number of edges you actually see. You take the difference normalized by the total number of possible pairs between Vi and Vj, and take the worst x and y. So that's some kind of measure of irregularity that you can introduce. And so the original lemma says that, it really, there are several ways. I put here just that you sum these and you get something less than or equal to epsilon. And the strong version, there are many variations on the strong version. So one of them says that, they usually start with not specifying one error bound, but a whole sequence of error bounds. And the idea is that, you possibly get this huge number of classes. It's bounded by the error bound epsilon, but it can be very large. And you don't get any compensation for that. So you get a large number of classes, and you still have this same error bound epsilon, which then somehow makes it sometimes not so efficient to work with, or not enough. And so what you can do is that you specify a sequence of errors. The epsilon zeros plays a special role. And then depending on this sequence, there is some k. And so that for every graph G, there is another graph on the same set of nodes. So again, we are replacing it by another one. And then there is also a partition into, at most, these K0 classes. And the idea is, or that's one way of saying you only change some small number, small fraction, epsilon 0 times number of points squared. You only change this number of edges. And after that, for all pairs, this measure of irregularity is bounded by some epsilon k, where this k is the number of classes. So you don't really know how many classes you will end up with, but the more classes, you should think of this epsilon k as maybe epsilon over k factorial or something like that. So something which goes very fast to 0. So it means that if you end up with a large number of classes, then you are compensated for by a smaller error between any two of the classes. Okay, so let me show you just a little rest, some pictures. So, because I think the regularity lemma is nicely explained in pictures. So here is a graph you start with, drawn in the traditional way. And here is, it's adjacency matrix. It doesn't really help much in visualizing things. But I replace the ones by little black squares and the zeros by little white squares, so I get this kind of crossword puzzle type picture. And this is now the, so I look at this picture, I consider this like the unit square, the whole thing, and so it's divided into small squares depending on the size of the graph. Now, so here is this picture, one such picture, and now what you can do, I mean, this doesn't say much, it sort of looks random. One thing you can do is to try to rearrange the rows and columns so that you may discover some structure, and indeed you can, if you rearrange it like I did, you can see that there's some structure. The upper left corner is denser and the lower right corner is sparser. And now you cut it into, in this case, just two pieces. I mean, the set of rows and the set of columns, which correspond to the vertices. You cut it into two pieces, and then you average out each of these pieces, and you get some different shade of gray. So these are the PIJs, these shades of the gray. These are these numbers that tell you the densities. And so the lemma says, okay, so let's look at the same thing on a little bit one larger scale. So this is some graph, already rearranged so that you see the structure. And then the idea is that if you, so this is important that to order the nodes appropriately. And now if you pick any of the squares here, then and you look at the corresponding square here, then this should be really random-like. What does it mean it's random-like? Well, it means that no matter how you rearrange it, you will not see these differences in densities. So this is what it means in this sense, that it's random-like. So that you cannot further rearrange this part to reveal more structure. And so this is maybe a picture about the regularity lemma that's good to keep in mind. The cheating is, of course, that for an arbitrary graph, you get here not 3, but a huge number of these classes. So you might think, I just wanted to mention, you might think that this Tower of 2 is maybe some shortcoming of the proof. So maybe if you come up with a smarter proof, but Tim Gowers showed that actually this is the truth. There's no way to, I mean, some version of the tower must be present. So there are graphs which really need this number. Okay, so I wanted to talk about show you one of the early applications of the regularity lemma, which is called the removal lemma. And it's a very elementary sounding statement in graph theory. It was found by Frieze and Szegedy just a little bit later. So the idea is that you have a graph which contains just a small number of triangles. The number of triangles of this graph, well, I mean, it's always proportional. I mean, it's a dense graph, so we expect the number of triangles to be a positive proportion of all possible numbers, and so it's of order n cubed. So we divide by n cubed, where n is the number of nodes. So we write it as epsilon prime times n cubed. And then the statement is that for every epsilon, there's an epsilon prime, so that if the number of triangles is less than epsilon prime times n cubed, then you can delete epsilon times n squared, so a small fraction of all edges, and destroy all the triangles. Now, this sounds like when you first hear this, you think that this, oh, come on, I mean, you just do some averaging or randomly delete some edges, and that should do the job. But in fact, it's a very, very difficult statement if you don't have the right tools. And in fact, it implies at least the R3n theorem, so which we have heard about. And in fact, the dependence, so if you look at the dependence of, I mean, say in terms of the reciprocals, so the dependence of 1 over epsilon prime on 1 over epsilon is, in all proofs, it's a power. It's a tower of height. Well, it used to be 1 over epsilon, and very recently Jacob Fox improved it to log of 1 over epsilon. It's still a tower. It's still a very bad dependence. By the way, here there is no construction showing that it really has to be this bad, but there's no proof either. So let me show you what does it have to do, because it's a very sort of typical of the simplest application of the regularity lemma. Let me try to show you how to apply the regularity lemma here. So here is some graph, and I already show you the regularity partition of it. And now you start deleting edges. I mean, that's your job. You have to show that you can delete a small number of edges and destroy all triangles. If there is a pair which is irregular, which is one of the exceptional pairs, you delete all the edges. You delete all the edges inside these potatoes. And you also delete all edges which are between pairs where the total density is less than epsilon. The edges in irregular pairs are at most epsilon n squared, easy computation. There are only epsilon k squared such pairs. And the edges inside these partition classes is, the number of them is again less than epsilon n squared, because k is at least 1 over epsilon. And the number of edges in sparse pairs is again at most epsilon n squared. So altogether you delete 3 epsilon times n squared, but it's the same thing. So altogether you delete a small number of edges. Now, I claim that by deleting this, you must have destroyed all the triangles. Now, why is that? Suppose there is a triangle left. Well, the triangle must go between 3 classes where the graphs between any 2 of these classes are, first of all, they are regular, so they satisfy, they're not exceptional, and they have a density at least epsilon. And now from this, one can show, it's not hard, that the number of triangles is what you would have in a regular graph, in a random graph, if these edges were put in at random. I mean, that takes an argument, I'll come back to it maybe, but certainly what it says is that the number of triangles is what it should be in a random graph. So that is the power of the regularity lemma, so that you can think of these parts, takes a proof, but in practice there's techniques to prove that these can be handled as random graphs. And if you put in edges here with density at least epsilon between these 3 pairs, you would create not only 1, but a large number of triangles, about epsilon cubed over k cubed times n cubed triangles. And so if you take epsilon prime to be this number here, then you get the theorem. So this is, I wanted to show you because this is somehow shows that you have really these 2 or 3 layers of the composition. So there is the underlying structure which consists of these classes and which includes the densities. Then there is the randomness where you can think of these pairs as randomly generated, the edges between those pairs. And then the third layer is an error, which comes like these irregular pairs, but those we ignore because it's small. Now I'm coming to other versions here. The linear algebra version, low-rank approximation. It's a basic tool in linear algebra. So the one way of formulating the regularity lemma, especially the weak version of it, is that, we can introduce a norm for a matrix among many possible norms. Here we work with what's called a cut norm, which is you sum over some submatrix the entries and take the absolute value and take the maximum of this over all submatrices. And then the regularity lemma in this formulation, the weak one, says that you can find a linear combination of a small number of matrices. Now these BIs are 0, 1 matrices of rank 1, so they just consist of a block of 1s and everywhere else 0s. And so that this sum approximates the given matrix in this cut norm, well, quite well. Actually, you see that the error is grows like, in this case, it's the number of terms you use here is polynomial in the error bound. So this is, in fact, even better than what the weak regularity lemma says. And the point is really that this is independent of the matrix. So the error is, well, I mean, it depends on some Frobenius norm of the matrix, but the point is that it's really small. So this is one version. It's a nice thing. We do this in linear algebra all the time. We want to find approximate matrices by low-rank matrices, and it's one way of looking at the regularity lemma. Here is an analytic version of it. We have some arbitrary subsets of the Hilbert space, K1, K2, and so on, some sequence of in the subsets of the Hilbert space. And and you have some function or some element of the Hilbert space F and some error bound. And then there is some m, which is less than or equal to 1 over epsilon. And there is a function f0, which is a linear combination of functions, one from each of the first m of these subsets. And here it comes the strange twist. Well, the way is that this function, the approximation is good. And the way you measure the goodness of this approximation is to take any function from the next prescribed set, and the inner product will be small. So it's a little bit mysterious, because somehow by working on the first M set, you sort of have to anticipate the next one and to get the approximation good in terms of the next one. I just remark that if you take, for example, the set of Vg by Vg matrices, and all the sets are the rank 1, 0, 1 matrices, then you get the weak regularity lemma. But if you take other sets with 0, 1 matrices consisting of a large number of blocks, you get the original lemma. And if you take even weirder sets, you get all versions of the regularity lemma. So this all depends on how you choose these sets, this K1, K2. Okay, so I'd like to get to another analytic version, and for this I will, okay, let me skip, okay, so I have to skip here a few. So let's look at functions on the unit square with values between 0 and 1. These are these crossword puzzle type pictures can be thought of these functions, but there the values are actually zeros or ones. Here I allow more generally any values between 0 and 1. And so these are called, sometimes called graphons. And the yeah, I think I will have to skip here. Okay, so for every such graphon, I define the norm, the cut norm of the graphon, as integrating over a square, And actually, well, I mean, the value doesn't have to be non-negative for that. I mean, this definition works for any function, any bounded measurable function, and I take the supremum of this integral over all rectangles. And then I can define the distance of two such functions. Well, it would be, of course, one distance you would get by taking the norm of the difference, this cut norm of the difference, but instead I apply a measure-preserving transformation. So basically the two functions are defined on 0, 1 on the unit square, but these are different copies of the unit square, and there are many measure-preserving ways of mapping one onto the other. And so I pick one where I take the where this norm will be minimum. So it's the best approximation. So the best overlaying of the two functions, basically. And here is the one statement of the regularity lemma. It says that there exists a step function, and a step function means that it's constant on rectangles. So for every function on the unit square, say with values between 0 and 1, there is, and for every epsilon, there is a step function with some bounded number of steps, which the number of steps depends only on epsilon, so that the step function approximates the given function with an error epsilon. So this is, we all know that a function can be approximated by step functions, but usually the number of steps is, there's no control over the number of steps. So the beautiful thing here is that this is an approximation in a uniform way. So there is a uniform approximation of functions by step functions. And the strong regularity lemma says something. I will skip that because I don't have much time, and I would like to at least come to this statement of the regularity lemma, which is, in a sense, the strongest statement. So the others, I mean, if you don't care about towers and towers of towers, and you just want an ineffective statement that there is, it only depends on epsilon, then this is probably the strongest statement. And it says that if you take those all functions on the unit square bounded with values between, say, 0 and 1, but any other two bounds would be okay, and you take this cut distance, then this space of functions is compact. And I have maybe just barely enough time to be able to show why this is, first of all, why this is somehow a very interesting statement, and second, how does it relate to the regularity lemma. So here is the idea of the proof. So if you take a sequence of functions, you would like to prove that this function has a limit. So the idea is that you take, in the first step, you take, here these are approximations of these functions. These are the step function approximations provided by the regularity lemma with, say, the same number of classes. So in each of these, there is and that means that the approximation, the epsilon, is the same. So these are approximations of the original functions by some bounded number of steps. And then we can go on and for each of these find a sequence of better and better approximations, here maybe k steps. Now, in each row we have a compact situation. These are functions, these are step functions with, say, k steps. So they are specified by k-squared numbers, the values on these steps. These are equal steps, and the values of these steps, if you specify them, you get these functions. So they will have a limit. So you can pick a limit because this is a compact description of these functions. And so you get some limit, which itself is a function with k steps, because it's just the Pij's that have to be convergent. And now there is a little work to do that these functions here, which are sort of finer and finer, come from finer and finer approximations, they themselves form a convergent, point-wise convergent sequence, and that's an easy consequence of the martingale convergence theorem. So combining, so what I wanted to point out is that the regularity lemma, the important thing is that it gives you a finite number of parameters with a fixed error that gives you, an approximation with a finite number of parameters. And once you have that, you can use compactness in each row, and then this implies compactness of the big space. And I think I have to stop here. So I would like to repeat my congratulations to Andre, and thank you for your attention.